All right. In our hopefully final conclusion and thrilling conclusion to the stars. Okay, we're talking about life cycles of stars, and we talked about the HR or Hertzsprung Russell diagram, known as the HR diagram for short. So we have your main sequence stars, which are most of your nuclear fusion stars doing their thing. All right. You have your cooler red ones, which are over here and are not as luminous, and gradually uh, you get these different colors, yellows and then blues as they get brighter and brighter. Um, white ones, white dwarfs you have that sit off the line over here, they're not very bright, you noticed, even though they are extremely hot. Okay, they're over toward the very hot part. Okay, because they're very small. Okay, and they're not visible to the naked eye, but they are really high temperatures. So they're hot temperature, but not very luminous because they're very dim. Okay, um, then you have your red giants, which are over here. Okay, and as you can see, red giants are much larger, but because of that they're very luminous. Okay, because and they're very high on the luminosity scale because they're very big, even though they're not real hot. Okay, they're cooler. All right, and then supergiants even more so are um, even larger. Okay, and they are a little warmer than the red giants. Okay, um, and so forth. Okay, and these are basically we'll talk about them in a minute. Are running out of hydrogen that they're so they can't do fusion much anymore, and this is kind of what causes them to go off here. And we'll kind of trace where the sun would go here in a little bit, but. Basically, let's just talk about what makes a star happen. Okay, basically the size of it, you have two forces are acting out. One is the gravity. As it gets bigger and bigger, it exerts a greater force of gravity on the particles around it and tries to pull them in or contract the star and get it smaller. In fact, gravity is the force that pushes the hydrogens together to fuse them into helium because the force of gravity is so strong it just shoves them together. And in doing so, a small amount of mass is released and changed directly into energy, and that's what fusion is all about. Okay, so gravity is the force that causes the fusion. Okay, fusion is the changing of mass into energy, but gravity is what causes it. Okay, now as the gravity pulls these together and they're cramming them together, that also increases the amount of heat. And of course, obviously, with the nuclear fusion and so forth, then the heat from that causes it to expand. Okay, so if a star is fairly stable, as our sun is right now, and a lot of these main sequence stars, that means those two forces are balanced, and so they're staying about the same. The star is not getting a lot bigger, not getting a lot hotter. It's staying about the same, and it stays about there. Now, the size of the star has a lot to do with um, how long it lives. And something, well, if it's a big star, it's a massive star, then it will live longer. And it's like, well, it kind of depends. First of all, there's some limits. If we're going to use big M means mass of our sun. So if a star is about, that's almost a tenth of the mass as our sun. If it's any smaller than that, it will not have enough gravitational pull to start that nuclear fusion in the first place, and it will never become a star. I mean, it being a planet or some other kind of a planet or some other kind of body, but it will not turn into a star. So it has to have a certain amount of mass in order to get enough gravity to start that fusion going on. Now, if you get too much, 100 times the mass of our sun, that's what the sun means, remember, then you've got so much force gravity, so much nuclear fusion going on. It's such a big thing. It just basically becomes a giant thermal nuclear blast. And so basically, suns only exist between, they have to be more than a tenth of the mass of our sun to start fusion. And if they got to be less than 100 times the mass of our sun, or they would just go out of control and just blow up and become a great explosion, and that'd be it. It wouldn't develop into a sun, so or stars, whichever you want to say. Now, generally speaking, you think, well, a larger mass is going to have more mass, so it'll take longer for it to burn out, if you will. That has more hydrogen in it. And so you think it would have a longer life cycle, but it turns out it's not actually that way because they have more mass, but that also means they burn faster. And so because they have such a strong gravitational field, it causes the fusion to occur faster, which of course makes them very hot, all that sort of thing, but it also burns them out quicker. And so We should be grateful, not that we're worried at 5 billion years left to go necessarily about our sun burning out, but we should be grateful that we have one of the lower mass stars because larger ones burn out faster, and then that would obviously cause some serious problems for everybody. So smaller stars have less mass, but they burn slower, and therefore they tend to have a longer lifespan. Okay? All right, now let's look at the sun and kind of take it through these steps and see what happens to stars during their life cycle. Now, since we're doing our sun, we're going to start down here on the Hertzsprung thing where our sun will go. Now, if you start up here, then we'll do a similar type of thing perhaps, and we'll talk about how it might be a little different. It might not end up directly here at the white dwarf, okay? But here we go. All right, so basically as the star begins to burn or run out of hydrogen, okay, it's using up its hydrogen, all right, the core tends to contract because you not have as much fusion going on, so that's what makes it expand. So it tends to pull in on itself. Okay, but as gravity pulls the star in, the temperature rises. Now, and you're out of hydrogen or you're getting low on hydrogen, so now as it gets more gravitational pull, starts contracting it, making more and more gravitational pull, helium burning occurs. When we say helium burning, basically what we're saying instead of taking hydrogen and helium, now we take helium and make it into other elements, in particular carbon. Okay, but can be others as well if things are added to the carbon. But basically, on the outside of the star, you still have the hydrogen helium thing going on, but on the inside, where it's been contracted and putting the gravitational force on it, now you have helium burning or helium being changed into carbon. Okay, now as you do that, all right. Um, it's going to get hot again. So now you're redoing fusion, except for instead of hydrogen to helium, now you're doing helium to carbon. All right, it's going to get really hot again. So it's going to expand. Okay, now overcome that gravitational pull and get so hot that it spins up until you end up with a red giant stage now, where it has expanded to a great deal. Now, if this happens to us at this point, Earth would probably blow away our atmosphere and basically crispy critter us. So we don't really have to worry about the sun actually blowing up. We'd be dead long before then. Okay, but like I said, hopefully that's not happening anytime soon. Okay, so it gets up to giant. Now, as it gets to a giant status and it burns up, it begins to cool down again. Now it starts to shrink. Okay, which once again, as they get closer together and you're forcing it down in there, it begins to cause heating again. Okay, until finally it's just, and so it burns that helium faster and faster until finally it's just burned out. And when it finally reaches that stage, it ejects plasma and gas and just shoots it all out into space. Okay, which is called a planetary nebula. Okay, it's misnamed in a sense because it doesn't come from a planet; it comes from a star. Okay, and it blows up. Okay, now that planetary nebula could eventually later come back together and form a new planet or a new solar system, but right now, no. Okay, now what's left is called a white dwarf, and it is a stellar remnant. Technically, it's no longer a star anymore; it's not undergoing fusion, and so it is just a white dwarf, which it is very hot and it would be luminous except for it's so small. Okay, and basically you have a large amount. Basically, you have the mass of a sun that's condensed to about the space of the Earth, and that makes it about 1,000,000 grams per cubic centimeter. Just think gold, which you think is very heavy, is 19 grams per cubic centimeter. On average, our Earth is 5.4 grams per cubic centimeter. Now you're talking about 1,000,000 grams, so it's extremely, extremely dense, and that is our white dwarf. And that would be basically where our star will eventually go and will be dead at that point. All right. Now, sometimes you'll have a binary system which there's two stars, and one becomes a white dwarf. And what happens is it can suction off hydrogen from the other star, which is still burning, and it can use that to start doing hydrogen into helium again. And it basically, this time though, instead of developing into a full star again, it will just blow up and have a little fusion reaction. And it can do this occasionally and draw some more hydrogen off till it gets enough and it blows up. These explosions are called nova, and they can occur at regular intervals. It's just a thermonuclear blast or fusion that occurs when it sucks that off. Okay. Now, this is for the our star, we said could follow this. Now, if you had a bigger star that is larger than that, more than 10 times as big as our star, that would be greater than 10 M sun, okay, then the carbon can actually begin to fuse together to make bigger elements such as neon and magnesium and so forth until you finally get iron, okay? And at this point, iron is the most stable element, so it can't do any more. If it does fuse anymore, it actually starts eating the energy and killing the star. So the fusion stops and it begins to contract. Big star, big gravity, it all pulls down into a small area. Okay. Now, keep in mind, though it's small, the mass is still the same. It's just becoming more dense in a small area. Okay. And usually they get down to where the electrons say, no, we won't go anymore, but and start pushing against each other. But now they actually fuse those electrons with the protons. And we know if you do that, you will make neutrons. And these are called neutron stars. So they're basically so much force that the electrons fuse with the protons and becomes neutrons. And this is what's called a neutron star. Now, if you have a ultra massive star, the super massive, it doesn't stop at the neutron stage. It actually gets to the point where it has such a strong gravitational field that it actually can suck in light. Okay, and if we go near a if we look at a black hole, it has such a strong gravitational field because this humongous star has now been almost to a pinprick of size. It's so small, it can actually suck in light. Now, light will generally go past it, but as it gets closer to it, it will start being bent, and there it reaches a certain point here where it will be sucked into the black hole. This is called the photon sphere, because this is where light gets sucked into the black hole, photon being light, and so it actually sucking in light. Okay, now once you enter that, now if we pretend that we get inside that photon sphere where light would be sucked in, say we were in a spaceship and we're getting in here, we're shooting light out. Well, as we get farther in here, light, if it's shot out, can still escape, although you can see it tends to get pulled back toward it. As we get farther, some of it gets pulled back, and as we get deeper into the proton sphere, less and less of light, only the directly straight perpendicular light can escape, and eventually reach a point where light cannot escape at all. This is called the event horizon. Okay, now notice all of this area here is not the actual black hole, which is down here at the bottom somewhere, but this is not a physical boundary. It's just the point at which there is no return. Nothing can escape, not even light, and this is what all gets sucked into a black hole. Now, what exactly happens inside a black hole? Well, there's theories, of course, but no one's ever been there, and so we don't know for sure. But that's strong gravitational thing. You have a supermassive sun that's gone to a little tiny point, but you still have the same amount of mass. That's what's hard to imagine, and therefore you still have the same gravitational field as it pull as it did before. But because it's so small now, the distance is very less, and so we know gravity increases as the distance gets less. And so now, instead of being a giant star, and so you're far away from the center of it, now you're right near the center of it. And so it has an extremely greater pull of gravity. The net pull of gravity is the same, but because the distance is less, it increases the pull of gravity. Okay? Uh, but there you go. And that is black hole. And once everything goes to black hole, it all goes black, and that's it. And we are done for the semester and for this lecture. Have a great rest of your year and your life.